again. Hello, everyone. Today we have a third presentation in our student paper award. It was prepared by Niklas, who will be presenting his paper, and he will tell you all about it. So go ahead.
Yeah, thank you for the introduction. I'm glad you all showed up. And yeah, so today's talk will be about neural arithmetic, and it will actually not be about teaching math to neural networks, but it will be about trying to extrapolate beyond the range of examples that were seen during training of a neural network. And it will then in the second part be about building transparent models. And I will go into more detail of what both of these terms mean after like a very basic introduction slide about what neural networks are, which you of course all do, right? We have some matrix vector that takes an input. We have a bias and we have some nonlinearity. And if we stack these things and build very wide layers, we get universal approximators. And what you can see, or what I'm trying to illustrate in this very complicated plot, is that if given a function, the black line, a neural network, which is approximated by the yellow line, can learn this function perfectly, right? And we can do this with any function. The problem is that if I show the neural network only examples in a range from, let's say, -1 to 1, it will learn this function very well. But outside of the training range, because it has never seen anything in there before, it will not extrapolate very well typically. And then the second problem that we will deal with is this black box nature of neural networks. And maybe an analogy of the black boxness of neural networks would be if I want to just tell if someone is a good person or not, and by opening their skull and looking at their brain, I will also never really find out, right? So, and it's kind of similar like that in the case of neural networks. So, and now in the remainder of the talk, I will first go into how can we do this extrapolation? How can we fix this extrapolation problem for certain kinds of tasks? And then how can we also take a stab at this black box problem? Okay, so another couple of examples of extrapolation problems. So, right, if I'm training a neural network on examples in these ranges from -1 to 1, or in this case from -3 to 3, I always, outside of the training range, the neural network does something, but not really, it's not really generalizing or not really abstracting the task in the way that we really want to. And as a sneak peek of what the neural arithmetic is able to do, and what we achieved with our paper is shown here. Now in green, you can see that if I just train this neural network in a range from -1 to 1, it can very nicely extrapolate outside the training range, both for this parabolar case and for the absolute value. For a periodic function like the sinusoid here, it's still not working, but that's already me showing you where our future work is going to go, right? So we can now, we can fix basically polynomials, but periodic functions are still a problem. Okay, and how do we do it? The first thing we do is we look at a subset of tasks, and what we were looking at was problems where we can assume that the underlying function is a composition of arithmetic operations. And then we can build neural network layers, new layers that have some kind of bias towards these arithmetic operations. And for example, for addition, it would be super simple, right? It's just a scalar product of an input vector x and a matrix and a weight vector w. And this is equivalent to just producing sums of inputs. So I can represent addition or subtraction like this if my weights are 1, -1, or 0, for example. Multiplication of inputs is a bit more complicated because essentially what I would want is if I have my input vector x, I would want to optimize power functions of x in order to be able to represent multiplication and, for example, division as well, right? So if I have x to the power of 1, that would be multiplication of or x1 to the power of 1 and x2 to the power of 1, that would be multiplication of two variables. If I have x to the power of 1 and x to the power of -1, x1 to the power of 1, x2 to the power of -1, then it would be division of two inputs, right? And typically in neural arithmetic layers, this is represented with this x block trick. And you can already see that this will be a bit, well, complicated because I'm going to get complex outputs from this logarithm if my input is negative. Okay, so the first arithmetic layer was called the neural arithmetic logic unit, and it's basically doing what I showed you in the slide before. It has an addition path and it has a multiplication path, and they fix this problem with negative inputs just by taking the absolute value in their multiplication path, and then they gate between those two. Yeah, so the problem with this setup is that I cannot properly represent negative inputs, right? But in theory, for positive inputs, I can now learn almost any arithmetic operation, addition and multiplication, as well as division. Okay, so let's see how this actually performs, right? We have a simple benchmark task, which is a function that takes two inputs and has two outputs. And each of those outputs is depicted in one of these plots over here, right? We have y on this axis and x on this axis. And then the first is addition. The second one is the multiplication we have here. The third is division. And then we have a square root. And if I just train a neural network now, a classic one that is not a neural arithmetic layer, on examples in a range from 0 to 2, you can see that here the light colors are low error. The dense neural network learns this very nicely in my training range, but outside it doesn't extrapolate very well, which is exactly what we expect, right? Okay, and now we can look at this neural arithmetic layer that I just showed you. And unfortunately, it's not much better, actually. Right, it kind of does something nice in the training range, but outside, it's still, we have a lot of dark colors, we have a lot of high error, which is due to this NALU having convergence issues. Because of this exponential and log in there, it gets very high gradients close to, for example, very small inputs. Yeah, but I mean, in theory, it could learn all these tasks, but in practice, it just doesn't converge to the correct solution. All right. Then we have the next guys, which try to fix this convergence issue by not gating between this addition and multiplication path, but by stacking specialized layers that can only do addition and only multiplication on top of each other. So again, the addition unit is basically the same as you saw before. It's a matrix multiplication multiplied with an input, right? So we have addition, and they actually clip their weights to be between -1 and 1, so that you can only represent preferably exact addition or subtraction. And then they implement their multiplication with an explicit multiplication layer, which can only do multiplication but not division, right? Because there's no, this exponent is not in here, but there's only explicit multiplications. Yeah, So that's that's the neural multiplication unit and the neural addition unit. And if we go back to our task, then you can see that this now learns the two tasks which it is specialized for almost perfect, or well, basically perfectly, right? Everything, this is completely yellow, so this is practically zero error. Unfortunately, it can't do division, and it also cannot do square root, right? Exactly because it has these explicit multiplications in its multiplication layer. Okay, and this is now in the last column, this is where we come in with the neural power unit. So we basically went back to the multiplication layer that we had in the NALU, which had this absolute value in here. And we replaced this by the actual complex logarithm, which will then be able to correctly process negative inputs. And also additionally has like an imaginary weight matrix in there, which is helping the thing to converge to the correct solution. Yeah, so and of course, after the layer, I just take the real part because I'm only interested in real outputs typically. And if I do now if I use Euler's equation on this, I can do some math to arrive at these two equations, which now represent a layer that can do multiplications and divisions of inputs, including arbitrary power functions, while processing negative inputs correctly, right? Okay, and yeah, right. So unfortunately, this setup also doesn't converge very well because for small inputs, the gradients in this layer become really, really small. So at some point, it basically just stops learning if it continuously gets small inputs in one input variable, which you can imagine, or I mean, the reason for this is if I multiply continuously by something small, right, then it's like multiplying by 0, and then my output will always be 0, which is not good, right? So what we introduced in addition to this complex stuff is a gate at the input that can just turn small inputs into a constant 1, so that the gradients can flow nicely through this layer and just ignore small inputs. Okay, so now we have our NPU that you can compare to the rest of the layers, right? It is not as good as the NMU on the specialized tasks that where NMU is like, I mean, it's like the specialist for addition and multiplication, so it's not really surprising that it's very amazing there, but we're kind of close. And in addition, we also get much better performance for division and square root. So yeah, this is the extrapolation part of the talk. And now I want to show you how you can actually use these neural arithmetic layers to build more transparent or explainable neural networks. And we tried this at an example of a fractional Sear model, which might have been the reason that our paper was so popular at NIPS, right? Because we were riding the epidemiological model wave. But the point is that an epidemiological model that models susceptible, infected, and recovered people is represented by a differential equation. And we can now train a neural network to approximate this differential equation just by looking at data from of these trajectories, right? And then typically what I can do if I use a classic neural network to fit a neural ODE to this data, right, which will take as an input measurements from Si and R and output the derivative information, and then I can start integrating over this thing and make predictions. I can make very nice predictions, but with this fitted neural ODE, I again have this problem that I can't really say anything about the actual generating equation of this problem, for example. If we use a stack of neural arithmetic layers and sparsify and use L1 regularization during training, what we end up with is something like this. So we built a neural network that consists of one neural power unit and of one neural arithmetic unit. And what you can see if we train this to ingest Si and R and output the derivatives and sparsify is that this NPU layer learns a product of S and I. These two are the two weight matrices that form a fraction like S to the power of 0.62 and I to the power of 0.57, and then form a product of those. And this is exactly what you can see here. Then it picks out just one variable and another variable. And in here, in the addition unit, you can see that it basically implements this matrix multiplication over here. So we have minus beta here, we have beta here, we have minus alpha and alpha over here, and data. And now you can see that basically like this is of course just a proof of concept, right? But essentially what we can do is we can take these arithmetic layers, sparsify them, and hope that they then converge to operations that represent my underlying functional problem. Yeah, so with a bit more work, right, we can probably say that we have successfully identified the differential equation that is governing this fractional SIR model. Okay, that's already it from me. Our future perspectives are going to be looking at trigonometric functions so that we can also represent periodic things, and then we want to extend this to do some like proper equation discovery on systems that we haven't where we don't know the exact solution, right? Yeah, okay, and that's it for me. If you have an application where you're like you really want to discover an equation for one of your systems, please let me know. And otherwise, thank you for listening, and I am looking forward to your questions.